Welcome back. I'd like to go over homework 6, matrix implementation of properties of relations. So this is going to be a pretty short video wherein I refer you to a much longer video. So the video before this has the algorithms you're going to need in detail. So look at that if you haven't looked at that yet. But in this video, I just kind of want to go over the nuts and bolts of getting this done. All right. So basically, I want you to write a program that looks at several relations and determines if they are reflexive, symmetric, and transitive. And if it is reflexive, symmetric, and transitive, then it's something we call an equivalence relation. And if it's an equivalence relation, then it has equivalence classes. And so I want you to print out what the equivalence classes are, right? So let's kind of go through the code and whatnot. So I've got a bunch of binary files that have this order. They're just binary files, that is, they're a sequence of bytes. So the first byte would have, well, it'd be value 4 in a byte, which means that it's a 4 by 4 matrix. And then there's the first row, 1, 1, 0, 1, and the second row, 1, 1, 0, 1, and like that. So it's just a string of bytes, but it'll read it as a sequential string of bytes from the file and dump that into a two-dimensional matrix down in here. Okay, so this is a two-dimensional matrix representing a relation, and this relation is reflexive, right? The diagonals are all 1. That's reflexive. It's symmetric, because when you got one over here, then you also have another one mirrored across the diagonal, and that's true for every one, right? This one here is mirrored over to this one here, and this one here is mirrored to this one here, etc. All right, sorry about the highlighting junk going on, but okay, so this is an equivalence. Well, it also happens to be transitive, which is harder to prove by looking at this, but it is transitive. And so it's an equivalence relation because it's reflexive, symmetric, and transitive. And so it has equivalence classes. And this row represents an equivalence class. And the second row is the same information. And this last row is the same information. Okay, and then this row here represents another equivalence class. Okay, so I've got some source code, and we'll look at that in a minute. I've got relation CPP, which is a template that has some functions missing that I want you to implement. And then I've got these input files that are binary files that contain the data I want you to analyze. So the first binary file, R1, I think is this relation right here. All right, anyway, here's what I want your thing to do. First, print out the relation, just dump it to the screen. Determine if it's reflexive and print is reflexive or is not reflexive. Determine if it's symmetric. Then calculate the product, okay, and print the product out. Then analyze the product to determine if it's transitive. And remember, the way you do that is for every non-zero element in the product, you have to have a corresponding non-zero element in the original matrix. Otherwise, it's not transitive. Okay, so this guy passes all three of these tests, the reflexive, symmetric, and transitive. So it's an equivalence relation, and the equivalence classes are these two lines down here. Okay, so go watch the previous video on the theory where I go through these algorithms in more detail if you haven't. But let's look at, well, I'll refer you to that right now. Let's see. So once again, there's another video that I talk about these in more detail, but here's the reflexivity check algorithm and the symmetry check algorithm. Okay, you want to implement those. Then right here is a matrix multiplication algorithm. So do that. And this is just the class notes, right? For the the lecture notes, whatever, for the class. And then there's a algorithm in here that determines the equivalence classes. So once again, there's a video already posted where I spend 20 minutes or so going through these algorithms. So look at that and watch that video if you haven't yet. All right. So So that's the stuff that's in the notes. That's about it. Let's look at the source code, which I've posted and pulled up into a project here. So yeah, this is the binary format of a file. In fact, we could open up that file and look at it real quick. So let's do that. By the way, these binary files, in order for your source code to read them, you have to dump them into the debug folder. At least that's the way it works in this version of Visual Studio that I'm using. Right, so this source code file will look for these files. And let's open one up. So you can open a file in the binary editor in Visual Studio. If you just open the file and this little drop down, you can select Open With, and there's a binary editor here. Where is it? Yeah, it's the first one, binary editor. We open that. There we go. So there's each byte in, just expressed as an integer, each byte. And then these dots, dots, dots would be the ASCII value if these bytes had ASCII values, which they don't. But anyway, the first byte is 4, which indicates it's a 4x4 matrix. And then these next 4 bytes are is the first row. And then these second 4 bytes is the second row, etc. Okay, I've written an algorithm to read this file for you, and it's at the bottom of the source code. It's in main. Here it is. So I'm opening a file, in this case R1 binary. Okay, this is just if you haven't ever opened a file, which you really should. Somewhere along the way your teacher should have had you opening files, but just in case, or if it's been a while since you did it, here's some C++ code that'll open up a file, and I'm using the read function here, and then all of these are going to be two-dimensional matrices, so I have a nested loop, and I'm reading in each byte and writing it to the matrix there. Okay, and yeah, so you have to post those, or you have to put these binary files in the source code so that your source code in main can read them. All right, let me run this. So F5, boom. Right now all it does is print out the matrix because I want you to implement the rest of this stuff. So let's go through that. Okay, so there's the byte sequence, and we looked at a binary file format with the binary editor. That's this thing right here. And in main, it opens the file and reads it into this matrix right here in this format. And then, yeah, which we have to imagine that there's these indexes on the matrix. 0 through 3 is the indexes we're using. And this is what it would look like in set theory, just communicating, what this represents in set theory. And then these are the equivalence classes. And the representative of the first class is 0, and he represents these 3 elements, 0, 1, and 3. The representative of the second class is 2, and he represents the element 2. So 0 represents basically this row, and 2 represents basically this row. Okay, bunch of C code in here, and this is given, and okay, this thing here I want you to implement. So take the algorithm that's in the notes for is reflexive and get it working in here. Right now I'm just returning a dummy value so it'll compile. And then this thing I want you to implement, that's in the notes. Okay, this thing here, squaring the matrix, I want you to implement that. Then you can use square matrix. That is, you can use the result of square matrix to write this is trans. You want to check in the square matrix and compare the elements in the square matrix with the elements in the original matrix to determine if it's transitive. And then here's an algorithm that that finds the equivalence classes. Okay, I'm describing it a little bit here, but it's also described in the notes, and then there's a video that goes through those notes. Okay, so study that, get that to where you understand that algorithm, use those other resources to do that, and then get this guy working. And then and print them out. Basically, printing them out, if you get to where you understand what finding them means, then printing them should be pretty easy. Printing them up in here, I've marked, the way I've done my algorithm, I marked who the representatives are in this little EC array. So I've marked the 0 element and I've marked the 2 element, because those guys are representatives of their respective classes. And then you just have to go to those rows, go to row 0 and print out the go back to R, go back to row 0 of R and print that guy out, and go back to row 2 of R and print that row out. That's how I did it. You could do it the same or a little bit different if you want. So so that's that. And then in main, it set up to read relation 1 binary file. I want you to modify this to go through all 6 binary files that I have for you guys. Some of them are kind of big. I think this R7 is pretty big. What is it? It's bigger than 1K. It's pretty big. Anyway, do this for all 7 of these guys. So this main will get pretty big because you're going to open up 7 different files. You could parameterize this. That is, take this file opening code and put it into a function and pass it the file name or something in a loop if you want, whatever you want to do on that. But run it for all 7 matrices, and then generate the output that I'm asking for, where where is it? Sorry, this stuff. Generate this, but for all 6 matrices here. Okay, all 7, I guess. There's 7 matrices. All right, so that's the nuts and bolts of what I want you to do. Once again, I've sort of skipped some of the details on how these algorithms work because that's covered in a previous video. So go look at those and refer to the class notes here, right? These notes here, which go through it in more detail. All right? It's not too hard. It's just iterating through arrays, working with arrays, 2-dimensional arrays, which isn't a super complicated thing. And just thinking about those arrays as relations. It's good stuff. It's really good stuff. Relating the discrete math theory to an implementation. So I hope you have fun with that. I hope this video was useful to you. See you next time. Thanks. Bye-bye.